Well, if you look at the program of this discipline, right, there is a midterm, right? There is a test in the middle. And so your final grade is a cumulative grade that aggregated from homeworks, this midterm thing, and final exam, right? Okay. I mean, well, there's still plenty of time to prepare. Please ask Ilya Andreevich or whoever also does the seminars for you, right, to go over the materials that you will need to prepare. Okay? All right, did I wake you up with this? All right. Okay, so let's get started. We're going to talk about graph partitioning algorithms today. And the first lecture, the first part is going to be a little bit mathy. I mean, we'll talk equations, we'll talk metrics, we'll talk algorithms. So this part of the lecture is dedicated to, well, spectral graph partitioning. And we're going to spend the entire lecture on this because this approach actually is at the root of several different methods for community detection or graph partitioning. And it is also quite sort of consistent and mathematically sound. You will look at other methods on the second lecture, which are more sort of ad hoc methods where there is less sort of fundamental mathematical background. This approach is actually quite nicely structured. And you can trace through sort of math how things work here. Okay, so first of all, just a reminder, and I think we talked about it last time, that network communities we usually call a group of vertices that are more tightly connected inside the group than between the groups, right? So that's what sort of the definition we used. And we said that, look, one of the ways to actually detect these communities is to think about this as a graph partitioning problem, or trying to find a way to remove some of the edges, right? And if we can detect somehow the edges to remove, then we can split this graph into communities, right? And the challenge would be, well, which edges to remove? Of course, if I draw it that way and you look at the picture, you'll say, yeah, of course, cut out those things. But if the graph is, the size of thousands of nodes or millions of nodes, you just don't see them easily. And so you need to figure out which edges you need to remove to split this graph into pieces, right? And so that's what the graph partitioning problem is about. So trying to split the graph, and that splitting will help us to detect communities, right? Okay. A little warm-up exercise. Let's say you have 2 points, right? A graph that consists of 2 nodes. There are how many ways to split this into groups? There's just one way, right? I mean, one group. Okay, actually, there is more than one way. You can have 2 and 0, yeah, and then there is like one node in one group, another node in another group. Now, if you have 3 nodes, how many options? 8? A little bit too many, I guess, right?
6.
Yeah. Well, actually, what you can do is, okay, here is one node, here 2 nodes, right? Let's say if we split into 2 groups, 1 node, 2 nodes, then there is another 1 node, 2 nodes, and there is another 1 node, 2 nodes. And then we can also split in 3 groups, right? Then with 1 node in a group. So, but you realize that it's actually growing very fast. If I start asking you, like, okay, if we have 4 nodes, how many ways? Then you can split into like 1 and 3, right? 2 and 2, and there are multiple ways of doing it. If there is, let's say, 5 nodes, then you can split into 1 and 4, 2 and 3, 3 and 2, etc. So there are plenty of ways to do it. It's actually a factorially large number. It's in some sense, it's the same problem as you deal with when you do clustering, right? When you try to group together different nodes, different points. So if we actually just try to bipartite graph, if we try to divide the graph into 2 nodes or do what's called bipartition, then that's the total number of ways we can do it, right? Again, you have 10 nodes, well, 10 factorial, and then whatever you split is into 2 groups, let's say 3 nodes and 7 nodes. That's how many of those combinations. But then you can also need to figure out, like, okay, we can, as I said, we can split into, if we have 10 nodes, we can split into groups like 1 node. We can split into 2 groups, we can split into 3 groups, into 4 groups, into 5 groups, etc., right? Up to number of nodes. So if I want to figure out, like, overall how many groups, how many partitions we can do, that's the number, right? And it actually even has a name, which is called, Bell's number. And just out of curiosity, if you try to calculate this, if you just have 20 nodes, that's how many different ways, different number of ways you can actually partition them into different groups. That's just huge. I cannot even pronounce this number, right? So why am I saying this? Well, the reason I'm bringing your attention to this is because, after looking at this, and this is just a factorial, the problem of factorial large combinatorial explosion, because it's kind of obvious from this that you just cannot go through all the possible combinations, right? That's the whole point. So if you want to detect groups, you just cannot go through all the possible combination of nodes trying to figure out what's the optimal grouping there. So you do need to use some sort of heuristics or some sort of approximations. And this is, again, this sort of the very well-known problem of this combinatorial fast growth. So how are we going to deal with this? Well, we're obviously not going to try to go through all the possible combination of the nodes to find out those groups, to find out communities. We're going to look into, first of all, we'll try to use some local properties, some locality, which is we're going to try to look at the nodes and its neighbors. And for this to be helpful to us, the graphs should be sparse, right? I mean, if the graph is dense, or quite dense, then the node is connected to a lot of other nodes, then for every node, pretty much every other node is neighbor, and so you have to go through all those possible combinations. So we look at the sparse graphs. But the good news, in the real world, most of the graphs we deal with, they are sparse, right? So the number of edges compared to the maximum possible number of edges are quite small. We also restrict communities to be connected. That also will put for us certain restrictions. And then we'll try to solve the optimization problem. And again, this is a combinatorial optimization problem. It's actually a very, very hard problem. So what we're going to do is, and actually to solve it, well, you need to figure out the criteria, well, which is like what we're going to optimize. And then you need to find out a way to optimize it, right? So you need to see what we optimize and then how optimize this. Now, exact solution, as we saw on the previous slide, is NP hard, right? It's just too many combinations. So what we're going to do is we're going to try to approximate this, and we're going to do it by either approximating algorithms or choosing particular criteria that is easy to optimize, or maybe using greedy methods. And greedy methods means when we have a criterion, we're not going to try to find the optimal, like global minima or global maxima, but we'll kind of restrict ourselves with a local minimum and local maximum, which might not be the best, but it's possible. Or we're going to use some heuristics that we know that works in practice. So having said that, just the major point here is when we look for graph partitioning or community detection problem, it is by itself, if we want to solve exact problem, it is NP hard, so we cannot do this. And that's why we're going to do certain approximations. And I mean, it actually goes pretty well with the definition of graph of community detection, because it is kind of imprecise definition, right? So that's sort of what we're going to do. So graph cuts, right? As I said before, as I mentioned here, what we want to do is first we want to figure out what we're going to optimize, and then we're going to optimize it, right? So first we need to find out some criteria for partitioning and then optimize it. So if I want to see if my partition is a good one, what would be sort of the most easiest criteria we could use? So you have a graph, right? And I'm saying, like, look, let's just start cutting out edges to split the graph into pieces. Let's say we want to split the graph into 2 pieces, right, into 2 parts. So what criteria can I use to see if the split is a good one or not? Clustering coefficient, yes, we can do that, definitely. And you will see we're going to use, well, not exactly clustering coefficient, but we're going to use some sort of density, local density, to evaluate things. But I'm looking for right now for something even easier than that. If I split, let's say, look at this. Let's say I want to split this into 2 parts. What edges do I need to cut? So I can cut this one. I can probably cut this one, right? Then we get this one part. This is another part. Can I do that? Yeah. Now, I can also do something different. I can cut this edge, and this edge, and I'll have this part and this part, right? Now, which out of these 2 approaches you think are better? The first. Why? Okay, so you just defined optimization function. You just said, okay, look, I want to minimize the number of edges I need to cut to split the graph into pieces. Make sense? So what you're saying is this. I want to remove edges such a way that the graph will split into 2 pieces. And I want to find those edges that overall will give me the smallest number of edges I need to cut. That needs, that will consist of the smallest number of edges. I mean, this is a metric. And we're going to see how it works, right? Now, that metric has actually a problem. If you just blindly try to use this, let's say, we decide to optimize it exactly like you said, right? And you run this algorithm, right? Imagine that you created this algorithm and you run it. Where do you think, what do you think it's going to do? Which partition is going to find for you?
It depends on where we start or which edge. For example, we can end up with 2 groups. In the one, we have only 1 node, like there.
So yeah, exactly. So if I actually, let's say I even go through all the possible sort of cuts, right? Eventually, if my criteria is the minimum number of edges that I need to cut to split the graph into 2 pieces, then I would, for example, cut out this one, right? Because it's just 1 edge to remove. We get this graph connected, and we get this, which is also, it's 1 node, but it's a graph, right? So just by itself, this criteria, will not work too well, right? Now, of course, we can, before doing this, we can actually, remember, we can use, like, for example, K-core decomposition, right, and get rid of situation when, when you have just single hanging nodes, et cetera, et cetera. But it's obvious that it will tend to try to cut out those sort of small pieces. Now, what would be the other option? How can we fix that? I mean, we can forcefully say, like, look, don't cut if it is, 1 node, right, or 2 nodes or 3 nodes. But that kind of not very, very nice from algorithmic perspective. So what we can do is we can actually monitor the size of the partition that's being cut out, right? And just say, like, look, for example, instead of just saying, just counting the number of edges, you can, for example, take the number of edges and then say normalized by the size of the partition that is being cut out, right? So, for example, here, yes, it's 1 edge, but we cut out the smallest one is 1, right? And if we cut it here, it's 2 edges, but this is 1, 2, 3, 4, 5, so it's 2/5 versus 1. So then it prefers this partition. So we can play games like that, right? Trying to find some function that would actually make sense to optimize. Does this make sense? All right. So in fact, there are like a lot of functions that have been proposed to do this. So the first one is actually just graph cut. That's precisely what we proposed at the beginning, which is let's just count number of edges that you need to remove to split the graph into two parts. And we're going to start writing formulas, and actually working with this approach just simply because it's the easiest one, but then it will be easy. Then we can easily replace it. Now, then there is a metric which is called ratio cut, where you actually take the partition, which is the number of edges, right, that crossing this cut, divided by the size of the vertex set of every partition, right? That's just how many nodes are in one partition, and this is how many nodes in the other partition. And you add them up. Then there is a metric which is called normalized cut. It is, again, the number of edges that crosses the partition boundary, divided, and this is called volume. Volume is a number of edges that originated from the nodes in that cut. Yeah. Oh, cut is, okay. If you have two partitions, if you have a graph and it's split in two pieces, right, then one piece of the graph, it's the nodes belong to the set V1, and the other nodes, the other part of the nodes belongs to the set V2, right? So the graph split into two sets. And what we do is we just count edges that connects those two sets. So this is just the number of edges. Yes, it's exactly the same thing, the same number of edges, but then we're normalizing by something. And here we're normalizing by the number of nodes in that set. And here we're normalizing by the number of edges that starts within the nodes of that set. So it's slightly, at first it's not obvious why you do it, but there is actually quite interesting theory why you do this. Plus this, if you do it that way, you can easily convert this optimization in a nice linear algebra problem. So we will actually, later on, we'll do this. We'll start with this one, then we'll show this one. Then there is also notion of quotient cut, where again, there is the same metric, which is number of edges, but then you divide it by minimum of those two volumes. Here, I normalize by the volume of one subset and the volume of another subset. Here I'm just taking minimum. This is actually a very good metric, and in theoretical computer science, people use a lot of this metric. Unfortunately, when you do calculations, it's actually very hard to use it because of this minimum, right? It's hard to, in linear algebra, it's hard to use this, the function minimum. All right. Make sense? Yeah.
Why do you count the edges that start in some part of graph? Because we split it into two parts.
Yeah. So we split it, yeah. So you split it into two parts. Let's say here is the cut, right? And so this is, let's say, first of all, the number of edges here, the number of nodes, 1, 2, 3, 4, 5 in this partition, and that's, we can count how many here. Now, the volume is actually the number of edges that starts from the nodes in this partition. So it is 1, 2, that starts from this guy. Then there is plus 3, 4, 5, plus 5, 6, 7, plus 8, 9, and here is 10, 11, 12. So it is, yeah, it is all the edges that starts on the nodes within your partition. And they might end in the same partition or might cross, well, the river, right? Cross onto another partition. That's what it is. And that's why it is here, it's this is number of edges that originates within your partition and ends anywhere. And it's also, you can actually easily see that this is just a number of node degrees within your partition. All right? Okay. Can you wake up your friend? Can you wake up your friend? All right. So, welcome back. I'll try to go faster so you will not fall asleep. All right. So there are a bunch of methods. So now we know this matrix, right? So this is a matrix that we want to optimize. Now we need to actually talk about how we're going to optimize it. The simplest way is so-called greedy optimization, and that we're probably not going to touch it for a second. Then there is approximate optimization, where we try to solve an approximate problem, and that's what we're going to do now. This is spectral graph partitioning. And there are some other algorithms that actually allows you to do this. But we know exactly what we're going to optimize. Okay. Now, this is probably the heaviest slide in terms of formulas that we have seen so far in this course. Let me try to explain you the idea, and then I'll just point out a few things here in formulas, but it's actually after that becomes obvious. So the idea is the following. Imagine for a second that we want to partition this line, this is our graph, into two parts, right? So the way I want to do this, the way I want to put this into formulas is the following. I want to assign to every node a label that will explain to which partition it belongs to, right? It can be partition 1 or partition 2. And my label is actually just +1 or -1, a number. The nodes that belong to say one partition will have the labels -1, and the node that belongs to another partition, all of them will have labels +1. Okay? 1 and -1. -1s and 1s. So, if, for example, assignment is like this, -1, -1, +1, +1, +1, it actually means that partitioning happens here, right? It is in between -1 and +1. These guys belong to one partition, and this one belongs to another partition, right? Now, this is just me trying to go from the language of graphs into the language of linear algebra. Okay, so my job, or actually your job, or algorithm job, would be to find those labels for every node. Because when you have those labels, that's, then the problem is solved, right? Then you know where partitioned is. So if I go back to this picture, what I'm trying to say is I want to assign to every node either +1 or -1, right? And that assignment will dictate the partitioning. And for example, if all these guys will get labels +1 and all these guys will get labels -1, I'll understand that this is how we split it. All right? So the job now is to determine which node has label +1 and which node has label -1. Okay? All right. Now, what I want to do, of course, in the spirit of our discussion, is to calculate the value of this cut, right? So how many edges I need to remove to split the graph into two pieces. And I want to calculate it in terms of those labels, or in terms of those indicators. And I'm saying that the cut value, if we use +1s and -1s, that the cut can be computed using the following formula. Let's think about this. What this says is we go through all the edges, and if we look at the both end of any edge, we take the label on one end of the edge, and we'll take a label on the other end of the edge, and we'll just subtract them. These are numbers, right? We can subtract them. So what happens is the following. If both of the labels at the end of the one edge is -1 and -1, well, this gets, that becomes -1 minus -1, it is 0, right? If both of them, both of the nodes here has the same labels, +1 and +1, this difference is 0. So it's not counted within the cut, which makes sense. We need only to count this one within the cut. Now let's look at this one. It's -1 and 1 here. -1 minus -1 is what? 2, right? I mean -2. It's squared, it's 4. Divided by 4, it's 1. So we exactly calculated the value of the cut for this picture. Make sense? Sort of? Kind of? Guys, this is like the key to the whole method. So let's make sure you guys understand this. Again, if we assign to every node the label +1 and -1, and we assume that all the nodes that has the same label belong to the same partition, and here is one partition and this is another partition, then the cut in between them, right, can be calculated using this formula. That's pretty much it, right? There is nothing else in here.
How do we indicate -1 + 1 at the start, just some random?
So what we're doing right now, we actually trying to calculate this optimization function, right? But then we're going to talk a little bit later, how do we actually assign this? Because what I'm going to do is I will say then, okay, now I do not know those labels. Let's find what they should be in order for this to have the minimum value.
We don't count twice, right? One edge.
No. If it's sum over edges, we count it only once. If we switch to sum over all the nodes, then to avoid double counting, that's why it's 1/8. So, but that's the point, right? What I'm just trying to say here, if we know that distribution, that's how we calculate the cut. But then the setup will be, well, now we don't know what should be here, but we want to assign those +1s and -1s such a way that this function is the smallest.
Why do we divide it by 4?
Oh, by 4 here, simply because the way we introduce it, it is -1 and +1s here, right? So if I actually want this to be my cut value, and the cut value is a number of edges that connects two partitions, here, if it is -1 and here it is +1, the contribution from this difference will be -1 minus -1, which is 2. It is squared, it is 4, so that's why I divide it by 4, so that it contributes only 1 to this edge count. That's it, right? Okay, so then there is like very, very simple sort of mathematical, I don't know, it's not even tricks, you just use some formulas. What you do is instead of summing over edges, you start summing over the nodes, but since these are I and j should be connected in this formula, well, the way to introduce this connection is by putting here adjacency matrix, Aij, right? So we switch summation over Ij over nodes, and we put here adjacency matrix. And then you do a little bit of manipulation, and you introduce Kronecker delta symbol, which is delta Ij, it's equal to 1 if I equal to j and 0 otherwise, and you can just rewrite your formula this way. Okay, so there is nothing happened here except for like some manipulation with formulas. Then eventually I can write this cut in the following way. The cut, which is just the number of edges that connects two different partitions, can be calculated in the following way. It is Aij is adjacency matrix, Si and Sj are those labels, and Dij is a diagonal matrix of node degrees. It is Ki, which is node degree, delta Ij, it is equal to 1 if it is the same node, if I equal to j, which is, or 0 if they're different. Okay? So that's pretty much all that I'm doing here. Make sense? So why am I doing here? Again, because I want to go from graphs to some optimization function. And I need somehow to express this, and that's the way to do it, right? I assign here +1s and -1s, and I'm saying, look, if that assignment is given to you, that's how you calculate the cut value. But because, I don't have this assignment, what I'm going to do is I'm going to say these are unknowns, and I want to calculate them. I want to assign to each s either +1 or -1, such a way that this function will have a minimum value. Okay? Now, yes? This one? Yeah, it's a node degree. It's a degree of node I, so number of neighbors. Node degree. Make sense? Oh, delta Ij, Kronecker symbol, which is delta Ij is equal to 1 if I equal to j and equal to 0 if they're not. I think we used it in the previous, some previous lectures. But again, this is mathematical formulation. This together gives us, I'll show you on the second slide, on the next slide, what it is exactly. Now, one thing to emphasize. So far, I have not simplified my problem at all, right? What I'm telling you is, look, here's the function. I want to find it minimum, right? Si and Sj are +1 or -1. They are integers. So this is the integer optimization problem, which is in p-hard anyway, right? So far, it's just sort of manipulation to get some structure to the problem. But there is no yet solution. Before we go further, let me just again explain to you what this difference is. And this matrix, the difference is this diagonal matrix minus adjacency matrix. It's actually appears very, very often within graph theory, and it has even a special name. It's called a Laplacian matrix. And that's what it looks like, or graph Laplacian or Laplacian matrix. So on the diagonal of this matrix, you have node degree. Off diagonal, you have -1s if the two nodes are connected. Otherwise, it has zeros. And I assume that in this case, my graph is unweighted. So let's see. This is graph 1, 2, 3, 4, 5. And that's what Laplacian matrix is going to look for it. On the diagonal, I'll have node degrees, right? This node has degree 1, this node has degree 2, this node has degree 2. So these are just node degrees. And off the diagonal, whenever two nodes are connected, there are -1s in there. And so because we have only neighboring node connected, there is sort of three-diagonal structure of the matrix. Is this clear what the matrix is? Guys? Okay. So this is, again, this is a very special matrix. It's, you take adjacency matrix, you put a minus in front of it, and you take the diagonal matrix with node degrees on the diagonal. And that's what you get here. It is very similar. It's the same diagonal matrix as we used when we talked about PageRank, for example. Right? We also use that matrix in there. So that's Laplacian. Okay? And that's called graph Laplacian. So moving ahead. Again, this graph Laplacian is D minus A, right? And here I'm just using matrix notation. And then the graph cut, the cut we have been working with, can be written as this 1/4 Lij, which is this graph Laplacian matrix, Si, Sj. And so if I think about now this S, Si, here is Si, and here we have Sj, right? Si is a label on node I, Sj is a label of node j. It can be either +1 or -1. But S by itself is a vector, right? It's a vector because you have, for every element of a vector, there is a corresponding, of course, node in the graph, right? So this is a vector. It's a vector, and this is just an element of a vector. This is a matrix. So you can write this as the following quadratic form, right? The transpose vector times L times vector. So this is like very, very second form how you can actually write this. And what you want to do is you want to minimize this with respect to S. So you want to solve optimization problem. Now, what I want also to do, I want to introduce certain constraints on S. In particular, I want to have this constraint. Sum of all Si is equal to 0. Now, what does it mean? Well, it means that I would like to have, well, if I force it completely, I would like to have the same number of +1s as -1s in my partition, which means I want to have a split of the graph that is balanced. It's not always possible, so this constraint will be satisfied, but weakly satisfied. So we'll try it. It will kind of force some balancing, but not very strict. Now, the problem is, again, so far I just introduced notations. I said, look, our graph cut can be expressed in the following way. This is an integer optimization problem. S is a vector of integers. I need to minimize this thing, and this is NP-hard. So it's pretty much what we have done for the last 15 minutes. In some sense, it's useless if I just leave it here, because it's not helping us. Because again, integer programming is very hard. It's going to be NP-hard. We'll not be able to solve it on large graphs. And so that's where the key idea came. And this idea belongs to actually Hungarian mathematician Fiedler. And he proposed it in 70s. And the idea was the following. let's look at this problem, right? Let's look at this optimization problem. And instead of doing this discrete optimization, so instead of solving this under constraints that S can take only plus or minus 1 values, right? So it's integers. Let's actually do an approximation. Let's assume that, or replace this S, let's assume that S can take real values. So it's not anymore plus 1s or minus 1, but it can be like 0.3, 0.5, 0.9, whatever. Okay? So we're going to remove the constraint of this being an integer programming. And what we're going to do is we're going to optimize exactly the same thing, but now I put it here x. So it will explicitly tell you that this is not an integer. You would say, so what? Well, it's actually a huge difference. Because now you can solve this instantly. Well, the question would be like, OK, well, if you solve it, you get some solution which has nothing to do with your original story, right? You were looking for plus, minus ones, and here you get some numbers. Now, in order for them to make sense, we also to add to this problem constraints. So first of all, we'll take this constraint that sum is equal to 0 and make this sum also to go to 0. And then this constraint that says every node has to be either plus 1 or minus 1, we'll convert into this one, which is the following. Imagine that each of these guys takes the value plus 1 or minus 1. Then you take this squared and you go and add up these numbers over the entire graph. What is going to be? What the number is going to be? The sum. Number of nodes. So this will add up to, and so what we want to do is we want to say that sum of the squares of our now relaxed variables has to be equal to n. And that forces those variables not to be very large. That forces them to be quite small because the squares has to sum to n. Okay? So we do this leap of faith going from here to there. Now, this problem can be solved very easily numerically. And then what we're going to do is we're going to go and round up those values. And if they are above 0, right, we're going to round them up to be 1s. And if they're below 0, we're going to round them to be minus 1s. So we look at this problem. We realize that it isn't hard. We cannot solve it. We relax it, replacing integer programming, integer optimization with real value optimization. And then when we got the solution, we round it up. And whatever we get here, we'll convert them into plus 1s or minus 1s.
And x be 0.
Yeah.
And x here be 0. Can we get like zeros or what's
Yeah, we can get zeros. There is nothing prevents it from being, but you'll not get all of them zeros.
Yeah, but like how we will assign minus 1s and 1s to this?
No, well, what's going to happen, I mean, I don't want to go into the details, but there is a lot of theory behind this story, and actually you will have minus 1s and plus 1s in here, right? I mean, negatives and positive numbers, you will have it, right? It just will be there. And it happens because this has to be satisfied. If you have only positive numbers, this will never be 0, right? So you must have positive and negatives here.
Yeah, and some zeros.
And some zeros, and that's okay. Oh, you mean perfect zeros?
Yeah, just we have
I don't think actually it's ever like going to happen in real life because we're talking not about integer programming, we're talking about real values, right? So you almost never get precise 0, right? But if you get, that's fine. Just make an assumption. Oops. Make a rule for yourself, like if it is 0, like go, put them into plus 1 category, right? Count them at plus 1. That's fine. So there are actually a little more to this, but for right now, I just wanted to show you this and a little bit explain how it's actually going to work. So if now, all of a sudden, I need to solve, instead of this problem, I need to solve this one, which is where I can convert to continuous problem, then what I do is this becoming my sort of Lagrange multipliers and constraint optimization. Do you guys remember Lagrange multipliers? What course was that where you used it? Come on. You're supposed to learn Lagrange multipliers sometime. In calculus, right? What is it used for? Optimization problem. How do you use them? If you have constraint optimization, right? You introduce Lagrange multiplier. You multiply your constraint by that multiplier. You add it to the function you want to optimize. Remember that? Sort of? I'm looking at this eyes like, yeah, maybe. Something like that. Well, look, that's what we do. You take your original function. That's your Lagrange multiplier. This is your constraint, right? So we add it up here to the function. We keep one constraint alone. Now, when you have this expression now with Lagrange multiplier, how do you actually do optimization? You take a derivative with respect to multiplier and with respect to the variable, right? So you take a derivative. If you differentiate this with respect to x, you get, and you have to equate this to 0, right? Because you're looking for optimum. Then you get this function Lx equal lambda x. And then you still have this constraint that x times the vector of 1s has to be equal to 0, which means really the sum of all x's has to be equal to 0. In a vector notation, that really means that vector x has to be orthogonal to a vector of 1s. But that's the same story. But the bottom line is, you take this optimization problem and it becomes eigenvalue problem. And you solve it. All right? Now, there is yet one more trick. Because of this structure of this matrix, the vector of all 1s is actually an eigenvector of this matrix. Take a look at this, an example. What does it mean that the vector of 1s is an eigenvector? I mean, can you actually see that vector of 1s is an eigenvector of this matrix? Come on. What's eigenvector? It's a vector that satisfies ax equal, lambda x, right? Now, what I'm saying is, for this matrix, the vector of 1s is an eigenvector with an eigenvalue equal to what? To 0. Let's see. Yeah, if you take 1s here and multiply by 1s the first row, what's going to be? What's going to be the value? Multiply this by 1s. 0. Multiply this by 1s. 0. This by 1s. 0. This by 1s. 0. So if you take this multiplied by vector of 1s, you get 0. So then you can say, okay, this multiplied by 1s is equal to 0 multiplied by vector of 1s. That's it, right? So it's an eigenvector with eigenvalue equals 0. Right? Now, the thing is, we don't want that eigenvector, because if it is eigenvector of all 1s, it means all the nodes belong to the same partition, right? And in fact, that that solution will violate this constraint, because we need the sum equal to 0. So that's why we avoid this eigenvector. So we take this is a minimization. So we need to take the smallest we need to take the eigenvector that corresponds to the smallest eigenvalue. The smallest eigenvalue here is 0, but it violates our constraints. So we take the second smallest eigenvector. I'm sorry, we take the eigenvector that corresponds to the second smallest eigenvalue. So the smallest eigenvalue is 0, and the vector that corresponds to it is 1s, and that violates our constraints. So we take the second smallest eigenvector. The eigenvector that corresponds to the second smallest eigenvalue. And that's why it is lambda 2 or x2. Okay, now that all looks like a crazy magic. Let me show you how it actually works in practice. By the way, there are a few things about spectral graph theory before we go into practical things that you might know. For example, so one thing is that the smallest eigenvalue is 0. The second interesting story is that number of zeros, if you actually calculate eigenvalues, corresponds to the number of connected components. Now, if your graph is connected, you have only one connected component, and that's why there is only one eigenvalue is 0. If your graph is actually consists of two connected components, the first and the second value will be 0. So there is actually a very, very nice connection between the properties of the graph and the properties of Laplacian matrix. Now, then there is, in fact, if we look at the second eigenvalue, if it is 0, it's disconnected graph. If it is 1, it's actually totally connected. And there are properties that allows you to estimate, for example, graph diameter from eigenvalues. But anyway, back to our story. So we look at the spectral graph partitioning. We look at the adjacency matrix. We think about this indicator vector. We compute our Laplacian matrix. We solve it. And then we just pick up a sign of those x values that are elements of the second eigenvector and assign them, assign those values to take the sign and assign them to the labels of the nodes.
If we have two components, we do it separately for one.
And if we do it, yes, and then we can do it like, and that's, okay, this is actually a very good question. There was a lot of surprising findings here. The obvious way is like what you said. If we have two components, we do it for one component and another, then we split in two pieces, and then we'll just keep splitting. That's one approach. But you will see that there is actually a slightly alternative way to do it. You will actually see that sometimes there is a way to split it not only into two pieces, but into more pieces right away. Again, guys, what I'm trying to do this, I'm just barely touching on the math behind this. But there is like very, very deep connection between linear algebra and graph theory. And if you're interested, there are like books on this, which really describes the behavior of eigenvectors and how this whole thing works. But again, for us, the key message here is the following: we try to solve graph partitioning problem. In order to do this, we convert this into linear algebra representation by assigning labels to every node. We're realizing then that in order to solve this, to solve the problem, to solve this label assignments, it's still an integer programming problem. And that's NP hard, so we cannot do it. So what we do is instead we relax it. We convert it into eigenvalue problem. Then we're finding second smallest eigenvector, right, corresponding to the second smallest eigenvalue. And then we're rounding it up, its values to become plus or minus ones, and we use that as the labels of our partitioning. Got the sequence? All right. So let me show how it works. It's the same in a never-ending karate graph. So here are the nodes, right? And these are node numbers. And so we can, for every node number, right, for every node, we need to eventually assign a label, plus 1 or minus 1, right, to do the partitioning. Now, what we're going to do with this Laplacian approach, graph partitioning, what we're going to do is we have a vector. This vector, we called it x on the previous slides. And for every node, this x will have some value, which is the second eigenvector, right? And then we're going to round it up. So let's see. If I actually calculate those values, what you see here on, well, you can barely see this. Horizontal axis is just a vertex number, 0, 1, 2, 3, 4, 5, well, the first vertex, second, third, and like 32nd. And these are numbers. Here is 0, 0, 2, and this is positive, this is negative. And every dot here, it's our node and the value that, in the second eigenvector that corresponds to that node. Make sense? And so what I'm going to do now is I'm going to say, okay, look, this is 0 line, and all the nodes that has the values above 0 will get the label 1, and all of them that below 0 will get the label minus 1. Okay? Make sense? So sort of, kind of. Okay. And, well, that's what's going to happen. It's kind of surprise, surprise, but it actually did a pretty good job splitting the graph. Now, it's actually getting even more interesting. We're going to do the following now. this is again the same computations. What I'm going to do is the following. I can take all the nodes in the graph and I can renumber them based on these eigenvalues, right? So, I mean, I had this numbering 1, 2, 3, whatever, right? What I can do is for every node, there is a corresponding value that I just calculated, the corresponding x value. And I can sort those x values and renumber nodes, now calling node number 1 that has the smallest x value, node number 2 has the second smallest x value, et cetera, et cetera, et cetera, right? So I can just renumber them. Can I do this? Yeah, I'm not changing the connectivity pattern, nothing. I'm just renumbering them. And if I do it, and this is, again, now they're like in random fashion, now I'm going to renumber them, and that means, you know, what you're going to see is from the left to the right, the values, the x values are going to increase. And that's what it looks like. Now, this is our split that we found originally. And here all the nodes that have values, x values above 0. And here all the nodes that have x values below 0. Right? So that's the split that we found. And notice that actually there is a pretty interesting and nice gap here in values of eigenvector. But if you look carefully, there is yet one more gap here, and there is one more obvious gap here. Now, that actually gives you an idea that, oh, maybe we shouldn't just split on 0. Maybe we should look for the gaps. And then what you actually see here is not 2 clusters, but maybe there is this one partition, second partition, and there is a third partition. Or maybe there is one partition, second partition, third and fourth partition. Now, this one is very small, but you know, could be. And that's actually another approach to graph partitioning. Oh, and I don't have the color. I haven't colored it, but that's what you can do here, right? Remember, when we start talking about this community detection, you know, etc., there is no sort of very strict way to define them. There is metrics that we try to measure. And so what I'm saying is, like, maybe, you know, this is the way to deal with this, and then instead of actually splitting into 2 parts, you can actually instantly split into 3 by looking at the gaps. And that's one of the ways to do this graph partitioning. Yes?
So based on this, what can you say about what the eigenvector values represent? So they are somehow close between nodes in the same partition. So that's about interconnectivity between them?
Well, yeah, so this is a good question. Again, you need to go into graph theory to understand a little bit better what's happening there. But if you just think about this, what we do, in fact, so we have the graph that lives into, you know, some high-dimensional world, right? We don't even know what dimensions are, but we can always embed the graph, for example, into the dimensionality, which is equal to the number of nodes of the graph. What we do here, we project this onto one dimension, because we assign to every node, we assign a coordinate. I mean, think about this. We started with these labels, but eventually we said, look, let's put an x value which can be, you know, can be a real number, which really means we assigned a coordinate to every node. Right? So now, if you think about this, what this is embedding of the graph into one dimensions. And so this is actually means these guys are close to each other in one dimension, then there is a gap in between the nodes, and their guys goes. So if you think about this and try to do clustering, yeah, that's your clustering will group this into one cluster, another cluster, another cluster. So that's what it is.
This is basically PCA.
Yeah, it is pretty exactly, except for it is PCA done on Laplacian matrix. It's not the adjacency matrix. If you can do it, if you want to do it in adjacency, it's not going to be that nice. And that's the trick. And like you, I think you were also assuming this, that can we do it instead of projecting, instead of taking the second eigenvector, we can also take the third eigenvector, for example, as another coordinate and embed this not into one dimension but into 2 dimensions. And then you can do clustering and find the communities in there. Yes, you can do it. And people do it. But it all started with this algorithm. So that was like sort of, this algorithm is circa, it's been developed in 1972, right? And since then, people keep building and building on top of it. Yes?
Can it be a measure of belonging to the class? Because we can see that these two nodes, 33, 34, that are like the center of one of the clusters, yeah, they have the largest value possible here on the graph. So they definitely the center of the cluster, and like the ones that are to the left, they're more like the second cluster.
Could be. Could very well be. So I mean, again, what we're doing is, if you think about this, it's a graph, and you assign a coordinate to this, to every node, right? And then you're interpreting it, and you can say yes, it's the centroid of the cluster, and everybody else is like built around it. So it is a way, and it's actually also a way to visualize graphs, right? Because after you assign after you assign coordinates to every node, right? You can draw it. You can draw those nodes. And if it's one-dimensional, okay, it's in one line, it's not interesting. But if it is, you do it in 2 dimensions, 3 dimensions, you can actually make nice pictures out of it. And it's one of the ways to actually draw graphs. Now, the trouble is, of course, when you get large graphs, it's going to be hard to draw. But there is a way to use this method to visualize graphs and to visualize community structure of the graphs. And I'm going to talk about it a little bit later in a few slides. Okay. Couple more things, guys. Now, notice, again, what we have done. We switched from this the idea of overall partitioning or splitting graph into pieces into this notion of, okay, I actually reordered my nodes into one line based on these values. And what I'm looking for is I'm just saying, like, where do I do a cut? So now I can actually go and say, okay, I cut here, 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 In between every 2 neighboring nodes, I draw a cut, and I can see how much that's going to, split it there and see how much it's going to affect my metrics. So what I'm saying is the following. Let's say we take this graph, which I had, and we renumbered all the nodes the way we just described using Laplacian algorithm. So now nodes are numbered, and here's the node numbers. And what I'm going to do is I'm going to calculate if I take the first node and the last 31 nodes as partitioning, and let's calculate what the value of the cut is going to be. Let's take the first 2 nodes as one partition and the last 30 nodes as a second partition, and calculate what the value of the cut is going to be. Let's take first 10 nodes as one partition and the next whatever nodes as another partition. Let's calculate what the value of the cut will be, right? So, and if I do this, I realize, by looking at those things, I realize, yes, there is a value of the cut. Here it is a small value, but then it's just I'm cutting out very small pieces. But if I go here, it's actually a small value of the cut. And remember, we're trying to minimize the cut. And, pretty good size of partitioning, pretty equal. And so what I'm saying is then probably this is the one partition, and this will be the other partition. And I can check, based on that approach, I can check all the metrics. I can check this cut, normalized cut, whatever I did there, ratio cut, and the conductance. And you notice, the little bit different shapes, but all of them have very explicit minima. And that minima, that corresponds to the optimal partition of the graphs into 2 pieces. And I could do, but the only reason I can do this is because I ordered the nodes, right? And the ordering came from this eigenvector story. Okay, any questions on this? So how are we doing with time? When do we need to have a break? At 30? So I have 15 minutes, right? All right. Okay, so that's general concept, right? What we talked about. There are other ways to kind of approach this graph partitioning problem working with linear algebra. So one of them is actually, if you look at this modularity, remember we talked about modularity a couple of lectures ago. We talked about, actually the last lecture and a couple of lectures ago, we talked about modularity as a metric that also can be used for graph partitioning, where, again, Kronecker symbol, it's 1 if your 2 nodes belong to the same group, and if it is 0, it belongs to the different groups, and it just literally counts how many connections you have within the group, within the cluster, compared to what you would have there if it was a random graph. Remember this story, right? Sort of, kind of. Yeah, this modularity thing. Okay, now what I'm trying to say is you can actually, instead of doing what I just described as this Laplacian exercise, you can actually do the same, very, very similar approach, take a very similar approach and optimize this function itself. So before we said we're going to optimize the cut. Here I'm saying we can actually optimize this modularity directly. Okay? And the way to do it is actually quite similar to what we described before on the previous half an hour. Again, the two classes, the same indicator variables, exactly the same story. You can actually, using this indicator variables, you can write Kronecker symbol in the following way. It's actually quite useful. I mean, people who do physics do see it a lot. But think about this: if I and j belong to the same partition, then it is plus ones, for example. It is plus 1 times plus 1 times plus 1 is 1. 1 plus 1, 2. 1/2 is equal to 1. And if it belongs to different partitions, this is minus 1 plus 1 is 0. Right? So it's a Kronecker symbol. So you can actually take this, and if you use this indicator variables, surprisingly, you can write modularity, this complicated formula, in the following way. And we just saw it a few slides ago, except for it was not this modularity special matrix, but it was the Laplacian matrix. So just to put this in perspective, the Laplacian matrix was introduced by Fiedler in 1972, right? And so back then, that was the first time a scientist used this, this linear algebra approach to solve the problem. Now, this is 2006, when Mark Newman, it's again the same Mark Newman that published tons of papers on networks, who said, oh, look, you know what? With this modularity thing, if I use this trick, I can actually convert this modularity, my modularity optimization problem, to also the same type of problem, right? Now, the only difference is, if you remember, with this modularity, we want to maximize it. Over there, we wanted to minimize. Here, we want to maximize. But then the idea is exactly the same. This is an integer. This is an integer programming, as I as j is assignment to the clusters. So we cannot solve it, exactly. What we're going to do, we're going to relax. We're going to introduce those, x variables, exactly the same as before. Now we get a quadratic optimization problem, which is eigenvector problem. Instead of Laplacian matrix, we have this strange and unusual, modularity matrix. And then you solve eigenvalue, eigenvector problem. And then the difference is now, well, first of all, it's a different matrix, and then you take the largest the eigenvector corresponds to the largest eigenvalue. The reason for the largest is because, again, you want to maximize modularity. Because modularity definition is, where is it? It's here. And when you have the best partitioning into groups, this has the largest value. And we discussed it before. So that's pretty much it for the modularity maximization. You can also use it directly through this linear algebra approach. And here is an algorithm, which is also very, very simple. You take your adjacency matrix, you introduce this class indicator vector, you compute this modularity matrix B, you solve eigenvector problem, and then you do the rounding up the same way, except for it is not for the second smallest eigenvalue, but for the largest, for the eigenvector that corresponds to the largest eigenvalue. That's it. That's going to be your partitioning. So, and this is an example of how it works. Again, we did exactly the same, but with this modularity maximization, and that's the partitioning it gives you on the quadratic graph. So, yeah, and that's modularity. That's the score. So, now when you have what we just described, and we spent like an hour talking about, is splitting graph into two pieces, right, into two groups. In order to actually detect communities, you might want to keep splitting, because if that's your graph, you might split it into pieces, then keep splitting until you actually recover the communities. It's one way. Another way, as we saw previously on this eigenvector picture, there might be a way to directly split into multiple communities if you have explicit gaps in that eigenvector. That's another approach. Or you can just go recursively. And then you get your partitioning. Now, one last thing which is actually worth mentioning is the following. Imagine that you can actually use this renumbering scheme, right, to renumber nodes in the graph based on the eigenvector. And then you want to draw adjacency matrix for this renumbered graphs. And the claim is that if you do this, and unfortunately you can barely see this, but it's all the same matrix, adjacency matrix. Here you can barely see, but there is a lot of blue points scattered around it. Now, every blue point, again, this is your node, and the blue point, it's adjacency matrix, so it's, if a node connected to a node, there is a blue point there, right? There is a point. So now what we're going to do is we're going to take this matrix, or that graph, and renumber all the nodes according to the eigenvector. If you do this, what's going to be happening is the following. The nodes that have numbers one after another, which is next to each other, according to our theory, belong to the same community. Right? If they belong to the same community, they are connected. And if they're connected, it's a dot, in this matrix. So, if I see on my adjacency matrix this type of a picture, it really tells me that this is one community because there are a lot of connections among them. That's another community, a lot of connections there. Then there is probably a bigger community but fewer connections. Then there is another explicit community. And so there is a way to see that in the adjacency matrix by renumbering the nodes based on that eigenvector. So you calculate that eigenvector, you renumber the nodes, and then you draw your adjacency matrix. And that's what you're going to see. And the reason you're seeing it, again, because here, every dot here is just connection of one node to another node. And if they're sort of randomly numbered, you don't see any structure here. But if you make numbering such a way that consecutive nodes will most likely be connected to each other because they belong to the same cluster, you will have very, very dense groups here, because that's like nodes numbered 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, etc. Make some sense? So, and what you see here is it's exactly the same matrix, it's exactly the same graph, but with what's happening is I have run this iterative graph partitioning algorithm on it and did sort of few passes of those eigenvector calculations, and eventually you see this, and you see that your graph has lots of community structure, which is not obvious from this picture. And in fact, when you have larger graphs, one of the preferred ways to visualize them is through adjacency matrix. Simply because, now this graph is of the size of probably 2,000 or 3,000 nodes. And it's actually very, very hard to visualize it such a way that, with your eye you will see clusters. But if you do this matrix visualization, then you will actually see groups of nodes that corresponds to clusters. And you actually see, like, in this particular case, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, well, maybe a little bit more of like explicit groups with a lot of connections within the group and some connections in between groups. And so you can actually see the structure by simply renumbering, reordering renumbering the nodes of the graph and then reordering matrix. Okay, I guess I puzzled everybody. No? Make sense? What's been done here? Okay. All right. We are done with this lecture. Just, oh, here is this original paper. Okay, I lied, it's 1973, but algebraic connectivity of graphs, that's where it's all started. Then, people came back to it in the 90s, 95, and then there is this paper on modularity, 2006. So this is actually a very, very big chunk of work on theoretical computer science and sort of graph analysis that deals with eigenvalues, eigenvectors of matrices and their connection to graphs and connections to graph partitioning. So there's like entire world in it. That's probably the most mathematical approach to graph partitioning, sort of consistent. On the next lecture, we're going to look at more of sort of heuristics, where people just tried this, and it worked, right? No proofs there. Here, there is quite mathematical sort of approach, step by step, of how you can actually, do this graph partitioning and why it might work. Okay, we're done. Let's take a 10 minutes break. We're going to talk about several other algorithms. First of all, we're going to talk about overlapping communities, which is slightly different from what we just discussed. And then we'll talk about a few community optimization, community finding methods. One of them is extremely popular, and it's probably right now is, the best one, right? This is called fast community unfolding. And then we'll talk also about yet one more interesting method, which is it's called walk trap method, but it's based on random walks, and so it's kind of nice connection to all the PageRank stories we had before. Now, again, when we're talking about all this type of community detection methods, I guess the key message is, on the one hand, yes, you wanted to detect communities, and there is a quality of your detection, right? If it doesn't detect well, that it's useless. But on the other hand, there is always a question about scalability of algorithms, right? Because very often, the graphs you're dealing, you almost never deal with the graphs like this karate graph, right, with like 30 nodes. Nobody cares about it anymore. You're dealing with graphs of thousands or millions of nodes. And so, which means your algorithm should be scalable. And when we look at the algorithm, it's a quality in terms of the quality of the detection of the communities and scalability, right? And unfortunately, for example, overlapping communities, that's actually quite different animal. We're going to look at it, but it's not scalable. So that usually works on quite small graphs. This guy is actually very scalable, and that's why people love it. This can also be scalable because this one allows you to actually detect local communities. So you don't have to analyze the entire graph. You can actually just say, okay, you know what? I'm interested in communities sort of within this region of the graph, and this allows you to do that. And so that's actually quite an interesting property. But anyway, let's talk about overlapping communities. Look, if we look at the graph on the left, that sort of reminds us about the graph partitioning problem, right? What we talked in the previous lecture. Maybe not so obvious, but still, there is this clusters here, cluster here, cluster here, and you can actually separate them by removing those edges, right? Now, there is a quite different situation right here. So what's different? D, yeah? There is this node D that if you look at this, there's a click here, there's a click here, so like sort of obvious communities, right? But this node is sitting here, and so you just cannot sort of cut it out easily. But that's, maybe with one node, you would say, okay, fine, well, let's let it belong to this community, we'll cut it out of here. It will break entirely, the community structure here, but well, maybe that's okay. But then, if you keep sort of thinking, you realize that there are like a lot of situations even like this, right? When the overlap is happening not only on the node, but overlap might happen along the edge, for example. Then it's just not easy, so you cannot remove this edge to split them. So this one, you can cut those two edges, and that's your community. With this, if you want to split them, cutting edges is not going to work. So you need to come up with something else. And so here the notion is that every node or pairs of nodes or edges can actually at the same time belong to different communities. And that's actually can happen, in real life simply because, if you think about this in, let's say, sort of Facebook story or any other social networks, you might have, a specific community that corresponds, to, if you think about even yourself, right? There is maybe scientific community, there is your family, there is this friends community, but they all overlap on you, right? If you belong to each of them, but then it also happens for somebody else, right? The friends, and et cetera, et cetera. So there is the situation when community overlaps, it can actually occur quite often. And people try to avoid this problem for a long time simply because it's actually, difficult to do this. And still the algorithm that I'm going to describe, it's kind of nice and cute and it actually works, but it's not scalable. And so you can run it on the smaller sets, but you cannot make it work on a much larger graphs. So the idea is the following. And the algorithm is called k-clique percolation, and we're going to talk about k-clique communities. So the idea is the following. Imagine that you can kind of detect a clique, right, very tightly connected group of nodes, and you can detect another clique, and you can detect their overlaps. And sort of, if the way it's shown here, you can even think about like having a clique and this ellipsoid showing very well connected nodes, and kind of it slides through and see if it can, cut out piece of very well connected nodes. Now, formally, how does this work? Well, it's going to be called k-clique community detection. So k-clique community is a union of k-cliques that can be reached from each other through a series of adjacent cliques. And two cliques are adjacent if they share k-1 nodes. So let me explain what this means. First of all, remember the notion of a clique, right? Clique is when you have several nodes, right, and there is a complete interconnect between them, right? So I'm going to talk about, here it's actually going to be talking about maximal cliques. Now, if you have a triangle, it's a clique, right? If you have 4 nodes, for 4 nodes to be a clique, it should be 1, 2, 3, 4, and the diagonals, right? Remember. Huh? No? Yes? Click? Click? Okay. So, if we have, for example, 2 triangles, let's say triangle CDB, this is a triangle here, and there is triangle CDF. They're a triangle, so it's a 3-clique, and they overlap on 2 nodes. So they overlap on the edge. So we have this triangle, and they overlap on this edge. And so they will be called 3-clique community union. If, for example, but here maximal cliques are not triangles. In fact, here is, we can look at, say, this is a clique, A, B, D, C, and this is a clique, A, C, F, D, A, right? And so they overlap by 3 edges. So you can actually, you can detect those cliques and just see on how many nodes they overlap. All right? Make sense? So when you have, now, this whole situation is interesting when the graph is quite dense. And so if you have those cliques, there is a significant overlap among them. So again, you can look, say, this is a clique, and these nodes form a clique, and then there's this triangle that they overlap on. So here's an algorithm. Find all the maximal cliques, and again, remember, maximal clique is a clique that you cannot enlarge anymore, right? Create this clique overlap matrix, threshold the matrix, and the communities will be your connected components. Let's just go through the example. That's going to be much easier to understand. So, this here there is a lot of cliques. So there is a clique. There is a blue clique. See that 5-star thing, right? This 5 pentagon here. It's blue. It's clique because it's all connected, right? Then there is a red one, which is 4 nodes. 1, 2, 3, 4. Then there is a yellow one, which is 4 nodes, right? And there is purple one, etc. So what I can do is let's say I can detect those clicks. And then what I want to do is I want to look at the click overlap. So calculate how many nodes from different clicks do overlap. Let's look at this blue one and red one. So, and this is a click overlap matrix. These are clicks that are just color-coded, right? So, and these are the number of nodes they overlap with. Now, click with itself overlaps with 5 nodes because, yeah, that's the size of the click. Now, this click, the red click, has 4 nodes. Here it is. Now, the blue and the red click, so this is a blue click, this is a red click, they overlap at 3 nodes. And that's what's written in here. Okay? Then if I take a green click, and I don't see it here, but it is, okay, that's a bad example. What else? Let's say I take yellow click. Here it is. I can barely see it also, but yeah, here is yellow click, and it overlaps with a blue click at 3, 1, 2, 3 nodes. And that's why blue and yellow gives us 3. All right? See how it formed, the matrix? Guys, make sense? No? You missed it, right?
No, I get it.
You got it? Okay, good. All right, so what you do is you detect maximal clicks, and when they overlap, you just calculate the overlap matrix. So the size of the matrix is number of maximal clicks versus number of maximal clicks, right? On the diagonal, it's just the size of that maximal click, like 5 nodes, 4 nodes, 3 nodes, 3 nodes, 4 nodes, 4 nodes. And what's here, this is like overlap, how much they overlap. Right? That's all we do. So we calculate this click overlap structure, and then we're going to say, okay, you know what? Let's threshold this at value k equal to 4. Everything that is above becomes 1s. Everything that below becomes 0s. But it's, I mean, we have to threshold k equal 4. We have to threshold at 3 actually, because that's the way it is described. Threshold matrix at value k minus 1. That's the way they want to do algorithms. So we need the threshold at 3, and everything which is 3 or above in this matrix becomes 1s, and everything that is below becomes 0s, and then this is whatever becoming connected components is your 2 clicks, I mean 2 communities. So they split it right now. The way this algorithm split this graph is into this community and that structure, right? So the challenge here is the following. Remember, on the previous algorithms, there was always sparse connectivity, right? So you have like few groups, communities, and they're sparsely connected with edges. And we try to remove those edges, detect those communities. Here, it's an opposite situation. You have communities that are very, very tightly overlapping, right? Cliques that are very, very dense cliques, they're overlapping. And you try to partition them this, very, very, when you have a lot of overlap. And that's why, you cannot simply cut out things here, easily cut out edges, simply because there's just too many edges. It doesn't matter where you look, it's everywhere very dense. Instead of going from the direction of cutting edges, they say, okay, let's take those parts of the graphs that we definitely don't want to split. It's click, right? Because you don't want to split click, because click, it's completely connected subgraph. It's a perfect community, right? So you don't want to split clicks. But what we can do, we can see if we have adjacent clicks, and if there is an overlap is not very large, then we can separate them. Does make some sense?
Could you comment on 2 values on the main diagonal? So to 3 and 3, main diagonal, 3,
5,
3
4,
and
4.
the next one, 3. The purple one. Why is it 0 after threshold?
That's weird. I don't know.
So it's just
Yeah, it's probably a mistake here. Yeah, it shouldn't be. Yeah, it shouldn't be. I mean, we're thresholding at k minus 1. All right, but I mean, this, guys, again, there's, as I described, in the previous lecture, I tried to convince that, over there was a lot of mathematics, right? which was like, okay, let's optimize this. This is optimization function. This is how we're going to optimize it. That's why it works. This is how we find optimum. Here, there is no math. Here, it's more of like intuition. Hey, we have those cliques that are very, very tightly connected. We don't want to cut them. Let's find a way to split things into pieces if we have very tightly connected groups, right? And so what they're saying is, here is a very tightly connected group, a clique, and here is another clique, and they overlap, right? And what we're saying is, if the overlap is much smaller than the size of the clique itself, then we're going to separate them. But if the overlap is very significant, then we'll keep them into one community. And so they build community out of cliques. Yeah.
Here on the right picture, are there some nodes that are included in one part and another part? Because it looks like more.
They should be. I mean, they could be, right? They could be. Because if you don't do this, you kind of break the overall structure. But I mean, I don't know. In this one, in this one, it looks like it's not. No, it is. Like if you look at this, see this one, right? Here they are, and here they are, right? So, they.
The one that is like up there, it is that purple that is lost. Yeah.
Yeah. Yep. Because it's not part of. Yeah. Because we're looking for communities. It's not that every node has to be in there.
Okay.
So it's different from what we did before. Before we removed edges and said, okay, here is the what we have. Here we're doing differently. We're saying, okay, here's our cliques, and let's see, if we can keep things tight, right, and still split them into pieces. And if something doesn't belong to anybody, well, it's not. Again, this is like very, very different approach. There is no math behind it whatsoever. It's just this sort of intuition. But eventually it actually does something for a particular type of graphs. It actually does a pretty good job. So here's an example of, again, probably it's hard to see here, but it does very nice partitioning automatically, right? Into these three groups, three communities with the one overlapping node, right? And so it's color coding it. Here, when I try to make it a little bit more. If K goes up, this is the size of the clique, right? You get, of course, sort of sparse representation because there are not that many cliques of high number. Here you get one clique and yet another clique, and there's like a couple more communities. Here yet another example of quite complicated and convoluted network and how it's been split into those communities. Again, notice that the whole point here is that you have some graphs that are very, very dense, right? But there are still communities in there. And I think this is from some I can see it, but yeah, it's protein interaction, right? Graph. And so notice there is no very clear or easily, say, cut from here to there. There are quite a few edges everywhere. And so that's why that's why you need to use different approach. If you try to just do graph partitioning as we did before in this graph, it most likely either fail or find very, very bad partitioning. Okay? All right. So that's just sort of, I wanted to give you a flavor of an algorithm that actually can work on dense graphs and just kind of work in a very different fashion from what we discussed before. Now, going back to like traditional graph partitioning, here is approach that probably right now is sort of a workhorse of most of the algorithm of software out there, and it actually scales and scales pretty well. If you notice this one, they did the graph partitioning on 2 million nodes, right? So that's actually a pretty big graph, and that's been done 10 years ago. And still, this is, with different twists, this is probably the best algorithm right now. So the idea is the following. This is, again, heuristic method, which means, we're just trying to do something which makes sense, right? We did it, it worked, we're happy, right? So, but there is no, like, fundamental mathematics behind it. So what's happening is the following. We're going to do, and I'm going to go through the steps, right, what the guys proposed. But the idea is the following. This algorithm looks explicitly at this function, at the modularity. But if you remember, within the method of that we talked about in the previous lecture, where we looked at this and tried to convert this in eigenvalue eigenvector problem and tried to look for global minima through eigenvalues and eigenvectors. In this case, what we're going to do is we're still going to monitor this formula, and we're going to make steps that are greedy, which means on every step, whatever we do, we'll try to maximize this. We'll try to make sure the steps we do with graph will increase this value until we reach the maximum, and after which we cannot increase it. Now, it's not necessarily the largest maximum. It's going to be a greedy maximum, which is it can be local, right? In a sense, there might exist much better configuration. We'll never reach it. We don't know. You just keep sort of walking and walking, keep doing and doing until we reach this situation where you cannot improve anymore, and then you say, well, this is our partition. And surprisingly, if you actually choose nice actions to do, this actually can be not such a bad result. Now, there are actually ways to check that is not completely sort of terrible by randomizing your approach and running it several times and just picking up the best solution out of those things. But overall, this is pretty much what the idea. Now, what does it actually do? It does the following. We start with, it's agglomerative algorithm, right? So what we talked before on the previous lecture, it was divisive algorithm, where we started with a graph, we split it into two pieces, right? And then you just keep splitting it. So we went top down. This approach goes bottom up, where we start with every node. It's the same as when you talk about clustering, it's agglomerative clustering, right? So what you do is the following. We start with assigning every node to its own community. So every node will be its own community. Okay? And then we'll look we take a node, pick up a node, and look at its neighbors. And say, okay, look, let's take this node and merge it with a neighbor into one community. Merge meaning like join the community of your neighbor, and see if that increases overall modularity, if that function becomes larger. If yes, boom, it stays with it. Done. Then you take the next node and you do the same thing. Check on the neighbors, see if you want to join one of the neighbors. If you join, if the modularity, overall modularity, if that formula decreases overall for the entire graph, then you don't do it. If it increases, you do it. Now, the trick is actually, I missed this trick, you actually not just do that, you try kind of joining each and every neighbor and pick up the one where the increase is the largest, right? That's sort of one of the twists there. And then you go to the next node and next node and next node. As you realize now, with this approach, you might get different results depending on from which node you start, right? Because I start with this node, I look at the neighborhood, I join one of the nodes into one community, I'm done. But maybe if I start from other nodes, there'll be already some structure, and when I get to that point, I will have to join some other community that will be more optimal. So depending on how you start, you'll get different results here. And so anytime you run this, you might get different results. But anyway, so you do this, and you just repeat until no more improvement possible, until you're stuck, literally, right? Until moving to, joining, until you go through all the nodes. And then what you do is those nodes that you put into one community, you merge them into like sort of super nodes, and just repeat this process. So let me just show you an example. You start with this graph. Every node belongs to its own community. Then you pick up one node and say, okay, look, if I join this node into one community, will the modularity increase or decrease? It will increase. Okay, let's see how much it increases. Remember that. Check if joining this guy is increase. Check if joining this guy is increase. Okay, fine. I know if I join this one, it increases the most. I'm joining this guy, right? Done with this node. Go to the next node and do the same, right? And then you just go through all the nodes. And eventually, you will get some sort of assignment, right? Then the next step would be, okay, here's the guys. They all belong to the same community. Let's replace them with the one node, with a super node that has the value that associated with it is actually the number of edges that are being collapsed, right? And all the green nodes will become this super node, all the blue nodes will become this super node, all this nodes remains the same, and the weights here are the number of edges that is in between, say, green community and red community. So you get this graph. It's sort of one path of the algorithm, right? 2 steps, one path. Then you do exactly the same exercise by merging this to the neighbors and converting them in super nodes. And you do this until you end up with like 2 nodes. Now, it's agglomerative, because the way it works, right? The tree it forms. It's probably going to be a logarithmic number of steps until you reach the 2 nodes situation. And because of this, it's actually fast, right? So you go, first time you need to go through all the n nodes. Next time, after you merge them, you go through like much smaller number of nodes. Next time, even smaller, even smaller, and even smaller. And so the complexity is just above n, but not that much. So which is actually very good. Make sense? Now, don't ask me why it works, right? Because there is like really no good explanation, except for on every step, I tried to do something which I believe is reasonable, which is, when I join other node, I join only the one that increases my modularity. And because I'm trying to optimize modularity, eventually, yes, it's becoming larger. Maybe it's not maximal. I mean, maybe you could actually get bigger value by doing something else. I cannot prove. But, it sort of works, right? If you run the same algorithm one more time, starting with sort of permute the way the nodes you start, you will get different result. But maybe quite similar, but different. All right? So that's what I mean by heuristic, right? Heuristica. So it is method that, every time you do this greedy optimization, every time you make a step in the right direction, but there is no sort of big picture behind it. Like you don't really understand, where you're going, or you don't really optimizing something very explicitly, right? I mean, well, you're maximizing the modularity, but you do it in a greedy fashion, right? Just every step, you increase it, increase it, increase it, and hope that eventually you get something that meaningful, all right? Now, surprisingly, this algorithm works and works really, really well. So it is fast because it is this agglomerative, and on every step it reduces the number of nodes it touches, and it just works and works. This is an example of a very large graph, how it actually detects different communities on a different level of resolution. And I believe Network X does have implementation of this algorithm. It's called fast community unfolding, or Luvian method, because I think it's the university where the guy was when he developed this. And so I would say at this moment it's probably algorithm of choice in practice, right? So the way it works. Okay, last thing, we're going to do one more algorithm. I wanted to point this out, to show this algorithm. No, first it also had mathematical background, but the good idea is also that this one you can actually run locally, which means, look, on the previous algorithms, the one we talked in the previous lecture, for example, what we did is we looked at the entire matrix, right? And we calculated eigenvalues, eigenvectors for the entire matrix, and we do this whole graph partitioning for the entire matrix, right, for the entire graph. So we looked for communities in the entire graph. This algorithm, the previous one, this fast community unfolding, it also runs on the entire graph. this story, you might have situations when you have a large graph and you want to detect communities in one sort of corner of this graph, right? Or in the neighborhood of some nodes. You don't really care about like the huge world. You just want, some piece of it, right? And that's where this algorithm can actually work pretty well. So one observation before we look at the algorithm is that if you think about, let's look at this graph, and you think about random walk, and again, random walk, remember, it's the idea that you come to a node, and then you have, let's say, with equal probability chances to follow to the next one of the neighbors, right? So imagine if you start somewhere here, right? And like if I'm asking you, what the chance that after 3 steps you stay in here or you move to this one, which is higher? Of course, you most likely stay in here, right? In some sense, it's like, again, if you think about St. Petersburg, like randomly walking, how easily it is to find a bridge that will take you onto another side of Neva River. It's not very easy, right? Because not that many streets that go to like big bridges. So random walk gets trapped in the densely connected communities, densely connected parts. So you start random walk here, it will spend most of the time in here. Right? It might end up getting to this node, but even if it gets to this node, there is still only one, what is this, 1, 2, 3, 4, 5, 6, 1/6 probability to get out, right? Otherwise, it's still in there. And so that gives you an idea to how to detect communities, right? The idea is very simple. You just start random walks, and you see how far it goes after some number of steps, right? And the community is actually determined by that boundary, right? How far it actually can go. And there are 2 ways to do it. One way is, in fact, just simulate this random walk, like literally just execute random walks. Say, okay, I start here, next step here, next step here, next step here, next step here. Okay, after 4 steps, I'm still within this. Start another random walk from this guy. 3, 4 steps, I'm still here. Started here, I'm here. Started here, okay, fine, I left, but this is 1 out of 5. And so on, right? And that kind of determines your boundary. Another way to do it is actually also through matrix multiplication, because there is a way to describe this random walk, this process, as a powers of the matrix, right? Because if you remember, adjacency matrix has a meaning of 1 step distance, and if, say, square of the adjacency matrix, it means whatever you can reach in 2 steps. And so you can actually use that. But that's the idea. And so, and there are like multiple algorithms that uses this idea. This one is called walk trap. Again, random walkograph. It's a uniform random walk, which means, from every node, we just uniformly let random step on its neighbor. And this is exactly the same thing as with PageRank, right? Oh, and by the way, this can be done also on directed graph if needed. Then this probability Pij power t is a probability to get from node I to node j and t number of steps. And you literally can compute it as taking your matrix to the power of t and looking at the values in between between I and j, right? Or you can like simulate it. And the idea is that 2 nodes belong to the same community if this value is high enough, right? Because if it means there is a high probability to get from one node to another in a small number of steps. And then you can actually define, distance between 2 nodes based on this idea, right? Let's say I want to define distance between nodes. Well, I go over all other nodes, either other nodes in the graph or other nodes in the neighborhood, and like I can measure distance from a number of steps from node I to node k and from node j to node k, and that can help me define the distance between 2 nodes. But this is a very particular implementation that this guy's proposed. The idea is much more generic, right? This random walk idea. And then what the guy said, okay, we can either do these calculations, we can estimate this probability either by direct computations, by taking matrix in this power and seeing what the values are, or actually doing compute random walks and just approximate it by seeing how many times you're starting from node I, ended at node k, right? In your random walk with t steps. And then you can define based on this distance between nodes, you can define define distance between communities based on distance between communities calculated as average distance between nodes within that community. And after that, you literally go back to agglomerative clustering, and you're saying, okay, this is an algorithm. Assign each vertex to its own community. The start is the same way as the previous algorithm. Then you just literally do agglomerative clustering. You compute distance between all adjacent communities, but the distance is based on this random walk. And so it means you don't compute distances between any arbitrary nodes, but only those that are reachable in some number of steps. Choose two closest communities, and in the first iteration, it's the two closest nodes, and merge them into one community or one node. You know, it's actually called the Ward's method if you remember data mining classes. And then just keep updating it. So, you know, if you do this, that's what's going to be happening. You know, you start with these nodes, they form one community, then you get more nodes adding to this, then more nodes, more nodes, more nodes, and then that's your partitioning of the graph, right? So it is again agglomerative approach to clustering, but based on the idea of random walks. And the good news again, this is you don't really need in order to detect those communities. I mean, if you're interested only in these communities and not interested in that one, you can just run random walk simulation in here and do this partitioning, and you don't really care what's happening there, right?
I do have outstanding nodes across them 16, so they are not in Blix.
I think yes. Yeah, it's interesting. I don't know. Probably. Yeah, this is strange. Probably they belong to like the bigger cluster. They believe they don't belong. You know, so there's one weak connection, so it should probably be part of this cluster, right? Like reasonably. Don't know. Maybe it's just again like color reproduction, and so it just says, okay, there's this big cluster where 16 is. Is it? We can look at here. Yeah. Yes. See, it belongs to the bigger. Yeah. They say it's part of. They say it's part of this big cluster, right? See if I look at this graph 16 where it belongs to, like it's the first split, this one big cluster, and this is another big cluster, and so it's part of this bigger cluster. Okay. Make sense? Okay. All right. Okay. So pretty much we looked at multiple different algorithms. I guess there has been a lot of work in this network community, network science community on clustering and graph partitioning or community detection. That's like sort of probably one of the most popular topics. And I would say what guys discovered that in the real graphs, the structure looks the following way. There is this usually core, which is, we already seen this, like K-core decomposition, how extract this core. There is sort of a big group of nodes that are very tightly connected. And then there is usually, you know, clusters sort of hanging out around this and slightly connected to the graph. And so when you do, if you want to do graph partitioning, if you want to disassemble this into pieces, what you do is usually the following. You do K-core decomposition to pull out this core, and then you work on pieces of them trying to detect clusters. And you know, there is no numbers here, but what they say is like in the typical graphs, this is one of the metrics. The conductance, we looked at it, it's cut divided by minimum volume of the set. It's actually minimum, typically, you know, reaches minimum when the size of the community is like around a couple hundred nodes. So they just claim that in most of the sort of graphs, like especially social graphs that we see, the community sizes is like around a couple hundred. That's sort of what's out there, right? So, you know, we would know. Okay, now this is actually 2010, which was now, gosh, 9 years ago, a long time ago. Back then, that was sort of the list of the different methods that were available for community detection. And I'm sure like now the list is much longer. Of course, this is not completely comprehensive. I mean, there's like, you know, it's probably the most popular methods. But what's interesting here is this complexity of the algorithms. That's computational complexity, right? And you know, some of those algorithms, and this is, for example, the algorithm for dense graphs. You know, like this exponential is number of nodes, which is terrible. It means, you know, it's not going to scale at all. a lot of algorithms like n squared, which is also really, really bad for computing. But some of them are like, say, n log square n. This is good, right? O of m. This is Blondel, which is O of number of edges. So there are some of them that actually can work on large graphs. Or here one is 0, O of n plus m. So these are the one you might want to use in real life. So again, there's two factors. One factor is how good is the algorithm in terms of determining, right? Determining your structure. And the second, how well it scales. Now, I wouldn't say, there's no one that is better than the other, in the sense that you typically, what you end up doing is you try different algorithms on your graph and just see which one will give you better results. After a while, you might get some sort of intuition, which one works better in which situations. Again, usually people start with the one we discussed, as Blondel, because it's fast and it gives us pretty decent results. But all of them worth a try if the size of a graph allows it. Okay. All right. And we're done with community detection, which is a big topic. Bunch of references, this random walks story. This is the original paper for this fast unfolding of communities and large networks. And this is the one that I would recommend. And then there are a bunch of other relevant networks stories. Now, this pretty much ends this module, right, this lecture. So I want to spend a few minutes to briefly go over what you learned, hopefully, maybe. Okay. The first lecture, network characteristics, power law, small diameter, high clustering. All right, so what's high clustering? What's it about? A lot of triangles, okay. What's small diameter? What's that story? Small longest. Yeah, it's either small longest shortest path, right, or it is small average shortest path. But what does it mean, small? Yeah, but okay, I have 20 nodes. What's small? Okay, I have 200 nodes. What's small? Logarithm, right? So it is. So the notion of smallness here, it's if you have n nodes, right? The large is going to be of order of n, maybe n over 2, maybe n over 10. It doesn't matter. But the small is the logarithm, right? If you have 10,000 nodes, then it is 3 steps. That's going to be small. 4 steps, right? 10,000 nodes. Then 4 steps. Okay. And the power law degree distribution, what's that about?
Small amount of nodes have most of the connections.
Right. And small amount of nodes have most of the connections. Majority of the nodes have low degree. But do you remember the formula? The probability of node having certain degree, what is it? Okay. Do you remember the law of like gravitational law from physics? No? Divided by the distance, right? There is a distance in there. Distance, right? What about Coulomb's law? It's the same except for the charges and the distance. So that's are all actually power laws because of the structure of the formula, right? So the probability is inversely proportional to the node degree, right? And the coefficient there is typically, we wrote it, the probability is 1 over k to the power gamma, and the gamma is around 3 usually. Right? That makes it different, of course, from Coulomb's and from gravitational law, but it's 1 over k to the power gamma. If gamma is equal to 1, that's your or if gamma is equal to 2, that's your Coulomb's law. All right, now network models. What's random graphs? Come on, think. Random, according to random, yeah. So what's random in there? So what? Okay, yeah. So you take two nodes and you flip a coin, and there is a probability, the probability threshold, and you either connect them or not, right? So that's one of the ways to build a random graph, right? So every two nodes are connected with a certain probability. Okay, what's preferential attachment? So it is a model that allows you to connect to, yes, so there is a high probability connecting to the nodes with high degree, but what's also makes it different from the random graph model. I agree, yeah. You were saying something, I couldn't hear you. No. No, what I mean is, if you have in a random graph model, it's a static model, right? The preferential attachments, it's dynamic. It's model of the growth of the network, because the way it's built is we bring a new node and it connects, right? We bring a new node and it connects to other nodes. We bring a new node and it connects, so it's a growing graph, right? So we have, like in random graph, it's we have fixed number of nodes, right? And then every pair, we go through each pair, and there is a probability they're connected. With the preferential attachment model, we start with a few nodes, and then we add the new nodes, and they connect, and then we take a new nodes, and they connect, and there is a preferential connection in the sense that they prefer to be connected to the nodes of a high degree, right? But it's a dynamical model, right? It's growing with time. The random graph model by itself, original, is not, there is no time component in it.
Didn't we discuss like two types of random graph models?
Yes.
One of them is like creating some nodes and
in random graph we didn't add any nodes. In random graph there are two types of models. One is you just go through all the possible universe of graphs with some number of nodes and some number of edges, and you just pick randomly one of those graphs. And that makes it random, right? You just go through all and you just pick up one. And the other story is when you go and the nodes are fixed, and for every pair of nodes you either connect them or not randomly, right? And these are two things, and mathematically they eventually, if n is large, they pretty much have the same properties. Now, small world model, what is that?
Small average length of path between two edges.
Yeah, but what's the model? These are we talked about like three different people and three different models, right? Three different sort of, again, a random graph, Ardor-Chevigny, preferential attachment, it's Barabashi, and then we also talked about the small world. There was another group of scientists who did that, and so do you remember the idea, what they did? So we have random, we have pretty good, well-connected graph which has high transitivity, so a lot of triangles, a lot of local connections, and you change some of the local connections into global randomly, and so you add randomness. And the idea is that there is a point there where, with some number of this reconnected, rewired links, you still get a lot of clusters, local triangles, but at the same time you also get like long-distance connections. And so the average path length becomes small because of these long-distance connections, but you still preserve pretty good density of triangles, right? And so that's what that small world model. And just to remind again, random graphs, they're pretty cool in terms of the mathematical properties, but unfortunately, the distribution of node degrees in there is, what's the distribution of node degrees in random graph? Gaussian, right? Poisson distribution. And preferential attachment model gives you power law. Small world, doesn't give you power law. But random graphs does not give you high clustering. Small world gives you high clustering. Preferential attachment doesn't give you high clustering, right? Okay, easy one, centrality measures. What's degree centrality? Okay, that's like pass or fail. I mean, there's just no way not to answer this question. What's degree centrality of the node?
It's a centrality measure based on
Yes, it's but what's node degree? What is node degree?
connections.
Number of direct connections from the node, right? Right. Number of neighbors, number of friends. So yeah, it's degree. What's closeness? What's closeness centrality? It is the centrality based on the shortest path, right? The number of shortest path that coming into. I'm sorry, not the number, but the length of the sum of all the shortest path from this node to all other nodes, right? And so if it's a central, that's going to be the smallest number, and you invert it, and that's going to be the closeness centrality, right? So it's the most sort of central in geometric sense. Betweenness.
It's based on the probability that the shortest path between two nodes will pass through this node.
Yeah, so it's how many shortest path goes through this node, right? And if it's like a lot of shortest path, then it's have high betweenness centrality. We talked also about eigenvector centrality in there. What was that?
It was about just symmetrics, but it was like based on the prestige of other nodes.
Yeah. So you know, yeah. So centrality determined not only by the number of nearest neighbors, but also based on their centrality, right? Okay. Now page rank. What's page rank? Oh, come on, people.
It's like centrality, but on the direct.
It's centrality for directed graphs based on. But what was the idea?
That a node with higher rank will be connected to other nodes with higher rank. So it's based on that.
That is true. That is true. But like sort of the initial story, like how did they come up with?
Random will go walk.
Yeah, it's a random walk, right? It's random walk, uniform random walk, pretty much the same as what we did today. But the idea was like random surfer, right? So it kind of started with a notion of surfing the web, right? Random surfer. It's called surfer because clicking on it. Okay, hits. What's that?
It was about hubs.
Hubs and authorities. The notion that every node can have two metrics associated with it. The hubness and authoritativeness, right? And one is really tells you about how much if it points to good nodes, and the other one tells you if good nodes point to you, to this particular node, right? And these are two metrics. Okay. Well, structural equivalence. What's that? What's that vertex equivalence of vertex similarity? What's that about? So it is about sort of geometric similarity, if you want, or structural similarity of nodes, and two nodes will be structurally equivalent if they have the same neighborhood, right? If they're connected to the same nodes, then those two nodes will be structurally equivalent. They're in some sense interchangeable, right? I mean, replaceable if they have exactly the same connectivity. And then the whole notion of similarity is based, vertex similarity is just the fact that sometimes there is no complete overlap of the neighbors, right? There is some degree of overlap. So you have 10 friends and 10 friends, 5 of them are common friends. Well, that's your degree of similarity, right? Sort of remember. Okay, well. Assortative mixing, what is that?
It's when we have a graph for some, for special connections, and if like nodes they connect to like nodes, if it's assortative.
Yeah. So this is the idea of if we have certain labels associated with nodes, we want to see the correlation in between connected nodes in a sense that if the labels of the connected nodes are correlated or not, right? So if you have, in other words, if like nodes connected to like nodes, in the sense that males connected more to males and females to females and males to females, that kind of story, right? If Democrats connected to Democrats versus Democrats to Republicans. And you can also think about this, it can also be not only with respect to labels, it can also be with respect to like any other attribute that the node has. It can be a numerical attribute, and you can think about, again, like with the social settings is an age, right? There is mostly, if you look at the social networks, you will see people of similar ages connected to each other. You think about your social life structure, you'll most likely, your friends have very similar income to you, so which means, your friend and the values of your income are correlated, right? By the way, that's how you can actually predict a lot of information, missing information in social networks, right? If I want to guess somebody's age, what do? Look at the friends. It's easy, right? And by the way, the funny thing, you cannot affect it, right? You can hide your age, your income, you can hide your location, but then you look at your friends who do not hide it. And that's all the information there, right? Now think about statistics, making it global, and that you realize that you can actually do very, very good predictions based on neighbors. And we're going to talk about this next module. All right, mixing by node degree, that actually means, the nodes with high degree connected with the nodes of high degree, right? So people with a lot of friends connect with people with a lot of friends. And the modularity, we talked about it today, right? This is a metric that allows you to distinguish if there is a group of people well connected, or if there is a, if the two classes belong to each other in groups. Now, network structures, cliques. What's clique? We talked about it already today many times. Yeah, completely connected subgraph, right? What is K-core?
So I can do it some kind of edges, some kind of three arrays that are
It's onion, peeling onion, remember. So K-core is a subgraph, right? Is a larger subgraph where every node has a degree greater or equal than K, right? Every node in that subgraph has a degree. So it is, it's your sort of neighborhood where if you go from node, every node you connected to has a degree equal to your or higher. But the way to construct it is by peeling the onion, right? Removing low degree nodes in the second level and second level. Okay, and finally, network communities. We talked about, overlapping, non-overlapping communities, right? And for non-overlapping communities, we talked about ways to do the graph partitioning, right? Dividing graphs into pieces. And we talked about the spectral methods. We talked about betweenness. The betweenness centrality method. It was a previous lecture. We talked today about Laplacian matrix and eigenvalues approaches. Then we talked about heuristic methods of community detection, and that covers that story. And I think that's pretty much it. So the reason I wanted to walk through this is because, as I mentioned at the beginning, there will be a test, right, on the seminar everybody like, there's going to be a test. In a seminar, I think it's not the next one, but in a one, I think it was going to be at the beginning of April, right? And it is a written test. Тест. Контрольная. Выбрать один из четырех, это был в детском саду. No. You'll probably, okay, you pretty much you're asking for like multiple choice or not, right? You guys got spoiled. When I went to college, there was no multiple choice. You just had to, solve the problem and not just guess 1 out of 4 with 25% chance of winning.
Since the beginning of the year, we didn't have any multiple choice tests.
Good. So, yeah, maybe it's going to, we can make it multiple choice, but then it's going to be a tough multiple choice. Look, seriously, I don't remember, honestly, what's in that test, but the idea is that you need to understand these concepts, and being able to do certain things like by hand, what I mean is, if you have a, I don't know, graph consisting out of 4 nodes, like 4, right? You should be able to calculate, and we say, okay, this is a graph partitioning, right? There's this community out of 2 nodes, and here's another community of, okay, let's say graph of 5 nodes. Here's a community of 2 nodes, and here's a community of 3 nodes. Calculate modularity. Now, I'm not joking. Look at this formula and look very carefully. The formula is easy, but it is not straightforward. If you never tried computing it using the formula before, you're gonna be wrong, okay? I mean, the first time you use it, it's most likely you're gonna do the wrong thing. It's not, I mean, it sounds like it is very trivial, but you need to actually do it once by hand to understand how it works, all right? So I do recommend you go and look in the textbook, the one that, I was showing, the Barabashi textbook. No, Barabashi. It's available online, right? And it does have quite a few worked examples of, say, modularity calculation, right? Or if we talk about centrality, again, we just discussed between the centrality, right? You understand what it is, hopefully, but then the question is, here's a graph of 5 nodes. Please compute between the centrality for this node. Again, it's sort of obvious, but if you've never done it, under time pressure, you most likely will forget to normalize this or do something. So those are very simple things, right? But you need to try them.
Are we going to have any proofs to do the test?
Any what?
Any proofs? Mathematical proofs?
Proofs? Oh, no proofs. No. That's a practical course. We don't do proofs here. We believe. You should ask your seminar instructor. He will tell you more, because I really don't remember the size. I mean, what we do. We have like.
Is it going to be prepared by you or by some instructors?
Well, it's going to be actually, we do, of course, have it prepared, right? We have certain versions of it. We have like multiple versions of it over the years, so we kind of mix and match things in there. We might add new problems, sort of remove some problems. It's just not ready yet, but again, there's nothing extremely difficult in there, but you need to spend some time preparing, just because, again, very simple computations. Like, how many of you actually do remember how to calculate eigenvalues of the matrix 3 by 3? Eigenvalues and eigenvectors of the matrix 3 by 3. How do you do this? Okay, how do you do that? Good. Matrix 4 by 4. So, anyway, like 4 by 4 probably will not give you, but 3 by 3 at least I hope you will be able to like calculate it. Again, if you haven't done it for like 5 years.
I had linear algebra course.
When?
Up here.
Oh, okay. Right. So you're lucky. Good. So you.
Don't give us 4 by 4.
Don't give 4 by 4 matrix. All right. Okay. All right. Anyway, any questions about this? The course, lectures. There should be online versions available. There's been recording happening. So if you're interested, send me an email. I'll send you a link.